All right, and then without any further ado, our next speaker is Jacob Finkelman. Jacob has used Rust since 2015 and has been a member of the cargo team since 2018 and is going to talk to us today about From Simple to PubGrub, the evolution of Cargo's resolver. Please make him welcome.
So this is not going to be quite as intense a talk as some of the others we've had today, despite how dense the code gets at some point. Another topic, these have desynced. That is annoying. Where's my mouse? There we go. I'm not sure how to kill that. So let's come back. I tried to get this right. I tried to be prepared. Nope, that's not helpful. That's even less helpful. Let's try this again.
There we go.
Yes. He's a good boy, even if the slides are not being a good boy.
What is the good boy's name?
Harley. Okay. And then I go into presenter mode. Does this work? Yay! Okay. Alternative introduction is, what does a dependency resolver do? Why is that a hard problem? Where is the technical debt hiding in such as even the simplest solution we can come up with? And why would we possibly consider a rewrite? Why is that the right solution? I'm Jacob Finkelman, but I've already been introduced. First off, thank you to the staff who's putting on this event. Mara is the one I've been interacting with the most, but that's only because I haven't had the opportunity to interact with the others who are working just as hard. Thank you to all of them. Next important thing, this is based on a true story. No primary sources were harmed in the making of this film. Historical events have been retold to make the narrative better, and code should be considered pseudocode to explain the point. Don't correct me if my syntax isn't right or if I'm using new idioms that weren't around when I say the code is coming from. So cast your mind back some 11 years. We are shortly before Rust 1.0, and you are working with Cargo or on Cargo. There isn't really a distinction yet. It's still a private project. Therefore, you are Yehuda Katz or Carl Lurch because you've just been hired by Mozilla to make a new package manager for Rust. This isn't the first package manager. It's the third or fourth, depending on how you count. The others are dead because makefiles really do work for the C and C++ community that most of our community comes from. So it's a bit of a long shot, but we want a package manager for Rust 1.0, so let's give it a try. We have a lot of important decisions to make. One of which is to design a dependency resolver. A dependency resolver is the part of the code that takes your list of direct dependencies and some source of information about what versions are available and what their direct dependencies are, and returns these individual crates need to be built in order for your project to continue. This is, of course, kind of academic, because given that you're the only two people who have access to the Cargo repo, there are no crates that are compatible with Cargo. There is no crates.io. You still need to write that. Someone could do a good talk about writing crates.io before you had any web libraries, because you didn't have any libraries because you didn't have crates.io, but that's someone else's talk. There are many decisions you need to make that are very important and will change the shape of what it's like to use Cargo. And none of those are about this talk. Those were thought about carefully and did not lead to technical debt. This talk is about the things you tried to keep as simple as possible so that you could move on with your life, and how that comes back to bite us because we succeeded. So the shape of a resolver, and luckily we have a very big screen because I did not lay this out nicely for you guys, is that it's a function. It takes in a vec of dependencies that need to be solved, that your root crate has some dependencies, and a registry, which is some API for figuring out what's available on crates.io, and it returns either a set of exact versions to build, or some kind of error. We'll leave it string for now because we're trying to keep things simple. So what's the simplest thing that could work so that we can write some tests that test all the rest of cargo? If you don't have any dependencies, then you're done. You just return the empty set, and it's all good. Now you can write a whole bunch of tests for all kinds of other hard problems. But eventually, you're going to have to come back to this. What if you have a dependency? Well, if you have a dependency, then you need to ask the registry what versions are available that fulfill that dependency. There's all kinds of hard engineering in that define what it's like to use cargo, which, as I said, is not the point I'm trying to make in this talk. You then go through those versions one at a time, and you see if they are compatible with the previously made decisions. Assuming that there's a little out of order, we haven't made any other decisions, but we will in a moment. Again, lots of hard decisions about whether you're like NPM and let lots of duplication happen, or like Python and only have one version per name, and all of that gets shoved into that function and is not the topic of today. And once you pick, if it works, and you pick a version, then it has some new dependencies that need to be added to the mix of what needs to be solved. So we have now successfully added one dependency off our stack, and we need to do all of them. So let's just use recursion, because it makes things simple. You need to change the name of the function because it's got a different signature, and you need the state that the previous calls had figured out in your API. And then if you have another thing, then you need to resolve it. If it works, you're done. You found a solution that works. Otherwise, you continue through the loop and try the next version. This is the simplest thing that could work, which is, I said, was our goal. But there's a problem, which is that we have two local variables, which are getting handed off to the recursive call and going to be saved for the next iteration of the loop to get handed off to the next recursive call. So we need to add two annoying clones here, which I know looks like an implementation detail, but it will come back to bite us later. So, okay, now we have something that compiles, and we have one more thing to deal with, which is what happens if you run out of versions to try, which is you fail. And because it's a recursive stack, maybe the next one will recover for you, or maybe this goes all the way to the user. But the only thing you can really say is we tried them all and they didn't work. So, okay. Congratulations. You have a resolver good enough to release cargo publicly and see whether people are even going to try using it. And this has a bunch of pros to what we've written. It is clear why it works. Its argument for correctness is that it tries everything. You can see in the code that it actually does that. It has some cons. Let's go into those details. First, those clones are going to bite us. We're cloning a lot of big data structures, and we would like to just slap RC on it, but it turns out that our access patterns mean that RC doesn't actually help that much. So we need a bespoke data structure for each one that clones the minimum amount. And you end up like using a linked list because it actually works pretty well here. And when you're saying you're using a linked list because it works well, you've got bigger problems. A lot of design effort goes into, over the decade, futzing with these structures to try and balance costs. But another thing is those access patterns. We are cloning because we might need it in the next iteration of the loop. But a lot of times, especially if you have a lock file, there isn't going to be another iteration of the loop. There's only one thing that could match. So it's really important that you check if your last iteration of the loop, and then the code's a little pseudocodey here, you take the value, leaving yourself with none so that you don't do a clone. Otherwise, you do the normal clone. Okay. And then we get real users who want more than 20 or so dependencies, and we blow the stack because we've built it recursively. So we need to rewrite it. It's a fairly mechanical rewrite, but to have an explicit stack that we push onto and then pop off of, and then update our local variables to match the ones we pulled on, except when we're going the other control flow, because we're no longer using control flow constructs. We're actually managing our stack ourselves. And this is mechanical, but it does lead to an unreadable mess where the control flow is buried in the middle of a loop, and where I'm sure you're thankful, we run out of room on my slides for code. So that is the last code we are going to show today, because we need to be thinking at a higher abstraction level. The code has gotten too complex. Ta-da! We have a resolver that can handle dozens of dependencies. It's good enough for people to actually, not just the test suite to try it, but for people to try it and actually figure out that cargo is actually pretty nice and we should actually like use it. And it works well when things go well. Less so when things go wrong. Let's look at an example of that. I'm going to go through this one a little slowly. We have an example. We have a libfoo. Libfoo has some dependencies. It depends on useful at 1.0. It depends on irrelevant at any version. It depends on problematic at any version. The names are suggestive. So the first thing we pop off that list is useful. We look it up. The only version that matches is 1.0, and we are still left having to deal with irrelevant and problematic. So we pull irrelevant off. We pick the latest version, which happens to be 1.9, and we have problematic on the list. So we pull problematic off. Turns out problematic adds something to our list because it depends on bad. Again, a suggestive name. So bad, it turns out, does not exist in the registry. So that's already a problem. So we go up the stack again, and now we try a new version of problematic, because maybe bad was added in the most recent version, but in fact, the previous version also depends on bad. So that fails. And then we try another version of bad, which doesn't work. And now we go back up the stack. Now, you and I are looking at this and saying, why did we stop here? Clearly, we should like take all of this together and say something like, every version of problematic depends on bad, and you depend on problematic, and therefore you can't be built. Irrelevant is irrelevant. But you've seen the pseudocode we were just running. None of that thinking is in that pseudocode. So we're just going to have to try the next version of irrelevant and see if that helps things. Which it obviously doesn't, because we haven't changed anything about problematic and the fact that it depends on bad. So we load in bad again and check, does it exist? No, it doesn't exist. I'm going to skip over the next 20-something steps where we discover that every version of irrelevant doesn't help, and every version of problematic has the same problem. So takeaways from this. Even in simple cases, we do an exponential amount of work if things go wrong. If we kept track of what went wrong, we could save a lot of time, and we could make better error messages that actually explain what's going on. We could also look to try and do some kind of synthesis where we notice and combine them into bigger statements that are more useful. But until we do that, we do not have enough information to give a useful error message. Let's do another example. I will make it shorter. We've now updated our dependencies. We now depend only on less problematic. Useful is 1.0, skip over. Less problematic at 2.0 also depends on useful. It has a caret dependency, so it could be on the latest version, but the 0.3 version doesn't work. Why? Because we already picked the 1.0 version. So we're going to have to try them. And at this point, we've noticed the pattern. And so we as humans notice the pattern. We should say, okay, it's beyond us. We'll just throw out, this isn't going to work. It's the same as the first case, except it's not, because the next thing we try works. The takeaways from this is we need to not only keep track of what went wrong, but exactly why. Because if you miss why, you get the wrong information. You skip over things you shouldn't, which is a correctness problem. And also, if you have the right information about why, that is helpful to the user in the form of error messages. So now we get to about 7 years ago in the Rust 20 era. I am a new to open source programmer trying to figure out how to contribute to the Rust project. I am looking to understand NP complete problems, and this is the only one that's been implemented in Rust, as far as I can tell. Nowadays, there's a talk on it later I plan to go to, but at the time, Rust is growing rapidly, and cargo is a key piece of that. It regularly happens that people add a dependency and everything just sits there, usually for a couple of seconds. Somebody donated a month of their laptop time to discover it wasn't doing anything. It never solved. So this is a problem I can dig into. And we know the shape from the previous discussions. So the first thing we're going to do is we're going to add what I called a conflict cause, which says every time we say, oops, we can't use that version, we store why we couldn't use that version. And then when we're jumping up the stack, we can say, is this problem still there? Well, then jump up the stack further. And so we can, and if we get to the top of the stack, we have just hit a problem, and we can explain to the users, there may be many other things that went wrong, but the last thing we tried didn't work for this reason, which when you have dozens of dependencies, is usually good enough to figure out, oh, if you were in this branch, then it must have been that other thing that was the problem. There are only so many things. A human can figure this out. The next kind of thing you can do is you can store them. Instead of discovering that bad doesn't work and then trying again and discovering that bad doesn't work, you can record, hey, bad isn't going to work. And then the next time you load in bad, you say, do I know any reasons why it's just not going to work at all? Okay, we can just pop up the stack again until we're no longer depending on bad. This is a fun data structure for supporting it, but that's a different. We can add a bunch of those generalizations, those optimizations. They're called minimizations because you usually end up with a simpler explanation afterwards than you started with. If A will cause B to be required, for example, you have a dependency edge, and we have a conflict for B, then we should be able to write a stored conflict of the form, we have a conflict for A. Of course, that's easier said than done. We need to exactly match in this generalization code the semantics of our just try all the versions. And if they ever come out of sync, then you get really obscure bugs. So where are we at? Pros. Cargo no longer hangs on any of the examples that people were actually submitting. This is really nice. We sometimes even give those OK error messages, which is a huge improvement. There are cons. Nothing about this is simple. I stopped sharing code for a reason. Lots of the pieces need to match. You can't just make a change somewhere and assume that the rest of it's going to compensate. They all need to have their different representations, and they need to match. And why is this all correct? Who knows? It seems to work. I understood each piece of it as I added it, but the results, I was a new programmer. So we are now in the, it's a mess and it's hard to maintain. If you're not sure what changes are safe to make, the next logical thing to do is, well, that's what tests are for. So let's go from a couple of example tests, dozens of example tests. It's really, but there are an exponential number of corner cases, so dozens doesn't seem so good. So extensive testing that randomly generates thousands of cases every PR and spits out a reproducible example if it doesn't work. And we verify it by having a separate implementation using a standard SAT solver. They're now available in Rust, that may not have the performance characteristics we care about for production, but we can use it in testing to see if we got a correct answer. And it is really nice. It prevents me shipping lots of bugs, mostly by preventing us shipping much of anything. So looks like things are hard. There are a couple of things that shipped. I'm exaggerating a little bit. A little anachronistically, this guy whose name I'm not going to be able to pronounce made a very good point in his PhD thesis that DPLL is an algorithm for SAT that roughly has the shape of what we're working on, that is correct because it kept track of all the things it tried, and when it runs out of things to try, it's correct. You might have side tables where you skip over things you know aren't going to work, but the fundamental argument is I tried them all. And there's an extension of that in the SAT world called conflict-driven clause learning, where you generalize some things and you end up with a proof that there is no solution. And he points out that is also profoundly simple because the proof is the only thing that counts. The thing you try next, you can just throw it out and start over. Anything you haven't proven, you try the first one you try. It either works or you prove that that doesn't work and combine it. So where do we store truth? We store truth in the stacks of things we've tried, the conflict clauses, and the exact semantics of the dependency code. We could combine conflict clauses and the stack if we always had one of those proofs for why something didn't work. That always is going to be a lot of work, but if we did it, we could even get rid of the semantics of dependencies if instead of having code that did it, we somehow represented them as a conflict ahead of time. So the code would say, we read from the registry some data, we turn them into conflicts, we add them to the conflict clause and the conflict cache, and then we continue evaluation until there isn't a problem. Of course, the representation I described for a conflict clause isn't sufficient to do an if-then statement. You need a slightly better one. This is where PubGrub comes in. We could have something simple if we just had better and we used it consistently. Natalie was assigned to build the package manager for Dart and did a lot of research and came up with some insights. One is that requirements are better thought of as a mathematical set of things that could match rather than an iterator of things that did happen to match. Of course, it's easier to say that if you're building things from scratch than if you already have a complex iterator that decides what matches and you have to match it. And she also generalized what we had been calling conflict, but other people had other names for, into incompatibilities, which can store all of the different kinds of things that we need it to. She has a great blog post announcing it, which is well worth reading. So the other important thing about incompatibilities is because they're mathematically defined, you can decide if a optimization on them is correct outside of the context. You can look at two incompatibilities and mathematically prove that a third incompatibility represents the other two, and then you can decide whether to use that or not. But none of this depends on the semantics of what dependency resolution you're solving, so you can test it independently, which makes a huge difference. Of course, in order to get all of these benefits, you not only need to have an incompatibility that represents your semantics, you also need consistently to use it and never have something that reaches through a back channel to see based on the order of operations. It is much easier to be consistent and disciplined if you start from a clean slate. So the PubGrub-RS library was born as a way to experiment and build an implementation. I have a talk from 3 years ago now about the details of how that library worked then, much of which is still the same, if you want to see that. The PubGrub-RS library is in production use. The Gleam programming language uses it for all kinds of things. UV, the very popular package manager for Python, uses it in production. So a lot of good feedback from them about what needed to be improved to make it work. And there are a handful of other semi-production and production projects that use it. It is actively being tested versus Cargo. We have a separate project that downloads all of the crates on crates.io and checks that the resolution you get if you use the Cargo resolver and some scaffolding around PubGrub are close enough to being the same that we're confident in it. We're still tightening the screws on how close that is and tracking down problems, mostly performance problems in Cargo and correctness problems in our lower-ranked PubGrub, but we're still working on it. And hopefully I can continue on that project goal soon and we can get a Z flag in Cargo. And so that is the end of my slides. That is the state of affairs. I'm open to questions. Yeah, the key takeaway here is that's what resolution is and why it's hard. Or if you're in charge of project goals, that's why I have a project goal that considers a rewrite when the rewrite should be your last possible option. Yes, now I'm ready for questions.
Thank you, Jacob. Do we have any questions? We have a few minutes. Okay.
Where do feature flags fit into this?
So, in the current resolver, they are one of the gnarliest of those details of exactly what things match your query that then need to have the same semantics in our representation of conflict. One of the causes of conflict is this version has this feature flag. And then you also need to track why does it have that feature flag. And if you wanted to support weak features, which is a fairly recent addition, you would also need to know both who added the weak feature and who added the thing that activated the weak feature. And that was complicated enough to get right, despite two of us trying pretty hard, that we just cut it out. It does not affect your lock file, and that is annoying, and I get complaints about it regularly, and it's because getting the semantics to match is just too hard. In the lowering to PubGrub, we solve it by representing them to PubGrub as separate packages. So foo is a package, and foo's feature bar is a package that has to match the version with foo and has some other dependencies, which we'll have to figure out how well that works. There's a reason it's not merged in yet. It gets the correct answer, and it is better at some performance problems that we care about and worse at other performance problems that we largely don't, but details to be figured out.
Okay. Since I'm already down here.
Thanks. So you said you were verifying against a SAT solver, but it wasn't performant enough.
Yes.
So I'm just curious, how not performant enough was it? But then I have a second question, which is, did you look into mixed integer programming at all for doing the solutions?
So the biggest problem with performance is less the actual performance of it and more the characteristics of that, what kinds of things are slow, what kinds of things are fast. Also, we want to pick the best for some local definition of best, which means that we're not looking for a SAT solver, we're looking for a max SAT solver. And you're right that actually mixed integer programming is often a better choice when you're looking for max SAT, but life gets complicated. Also, when you lower to SAT, we need to pick one of these ends up being a lot of XOR requirements, which is the thing where SAT solvers fall over. So by building our own, where that is one of the basic operations, we remove a lot of the slowest cases at the loss of not having a huge community of people helping us optimize it.
Okay, I think there was somebody up here somewhere.
The other thing that happens with a SAT solver that hopefully won't happen as much with PubGrub is that SAT solvers will say, a nuisance variable you added over here to express your exclusive OR is incompatible with a nuisance variable over here about a different XOR, and explain that to the user. How? What do these variables represent when it's done simplifying it? I have no idea. How am I supposed to explain that to the user? Whereas PubGrub, at least the first two layers of abstraction are things people know about. When you say this set of versions, that is a version requirement that is in a syntax you had the user write. And when you say an incompatibility of this shape, most of those, at least the two-length shapes, are things that a user knows about. A negative and a positive is a dependency edge. I don't care where it came from. You can explain it to the user as A depended on C. We derived that from something, but that we can explain. Yes, it's isomorphic to all the others. There are cases where our explanations fall apart, but I have hope that it will be interpretable for the simple cases people actually hand us.
Yeah, sorry if this is repetitive, but maybe this is going to be a simpler version of this question. So as I'm understanding it from this, it's essentially kind of PubGrub is a custom max sat solver for this problem.
Right.
What is the motivation for building it from scratch in Rust as opposed to interfacing with existing sat solvers? Because I do know in other contexts, I'm not super educated, but as I do know in other contexts, right, you might just interface with an existing sat solver that someone's already defined, and that runs relatively fast.
Yeah.
Is it a performance problem? Is it about explainability? Is it fun?
It's a little bit of all three. There are performance characteristics that are different that we don't have control over. There are trying to get the error messages to make any sense. There are advantages to writing it ourselves. The reason to rewrite it in Rust as opposed to using a PubGrub implementation in another language is that while PubGrub is algorithmically fast, the details really matter, and we can write it faster in Rust than any of the other implementations. Small VEC optimizations turn out to be really important, and they're annoying to do in a garbage-collected language. You've got one behind you.
Perfect.
Hey, Jacob. Thank you for the puppy tax to start the presentation off. So right now, PubGrub is being, you said, verified against the existing solver. There's a lot of correctness checking. Meanwhile, UV and Gleam just said, good enough, let's send it? Or is that because you're trying to maintain back compatibility? Is there a different standard of correctness? Like, why are they just full steam ahead and, like you're still doing work on this?
We have extensive tests of PubGrub. A lot of the testing infrastructure that worked for Cargo could be copied over to the PubGrub implementation and simplified because it's a simpler model. So it has very extensive tests. For the problem it solves, I'm quite confident it gets the correct answer. UV did extensive testing for the extensions they needed to make. Does it get the correct answer that got them comfortable? The part where I'm still testing and moving slower than other people would like me to is when I modeled Cargo's dependencies into PubGrub's incompatibilities, did I lower it correctly? Or do I have slightly different semantics between them, which means that PubGrub thinks there is an answer when Cargo thinks there isn't, or vice versa?
Okay, we probably have time for one more. I see one down the front there.
Riffing off of what you just said, would it be feasible to, say on like nightly builds, run both resolvers and then just report when they diverged, if they ever diverged?
Yes.
Is that the plan?
That is, currently we need a Z flag that even gets it in so that we can run it internally. I would assume, but it is up to the rest of the Cargo team, that one of the next stages is it runs in shadow mode, and if you turn on the Z flag, it tells you if there's a problem, if there's a mismatch, or it tells you to open a bug report. And then we'll switch to, because PubGrub probably has more correct, if not more readable error messages, if there's a correct solution and they agree, wonderful. And if they both agree that there isn't a correct solution, we show you PubGrub's one. And if they disagree, we tell you to make a bug report. And then we'll have to see if we can actually remove the old code, or if we end up needing both of them to support old versions of the resolver. But this is vaporware several stages down. But yes, that is the goal.
All right, I'm sure Jacob will be more than happy to talk to people about this for the rest of the conference and at the all hands. But for now, let's thank him once again for his time.